This is the podcast for the journal Neuropsychopharmacology. I'm Cynthia Graber. For years now, scientists have noticed a rather strange phenomenon in animal models. Scientists would stimulate dopamine production in the brain, but once the stimulation was over, the dopamine would remain.
I don't mean a second or a minute, like 15, 20 minutes till it was gradually back to baseline, which is odd.
Bita Moghadam is chair and professor of behavioral neuroscience at Oregon Health and Science University. She says that when dopamine is released, dopamine transporters take the dopamine back up into cells so it can be synthesized and broken down. So scientists had assumed that the dopamine that remained for those 20 minutes was just leftover dopamine from the original activation. But in theory, the dopamine transporters should be more efficient in taking up the dopamine.
That was the phenomena that we had. We had it years and years ago, and we kept seeing it in different contexts. So we started essentially figuring out why is dopamine staying up.
The result is a study she and her colleagues recently published in the journal Neuropsychopharmacology titled Burst Activation of Dopamine Neurons Produces Prolonged Post-Burst Availability of Actively Released Dopamine. Dr. Moghadam, for the first experiment, you stimulated the animals electrically and optogenetically. Then, after stimulation, you blocked dopamine release with the drug PTX. What did you see?
If this was dopamine that had already been released when the animals were doing the task or when we were driving dopamine cells, then by stopping signal transduction and the release of new dopamine, then there should still be a lot of dopamine around. This is something that happened 20 minutes ago, and I'm still seeing an elevated dopamine release. If I block release, then it shouldn't do anything to my signal, right? But we blocked signal transduction and active release of dopamine, and the signal went below detection limit. So this meant that, it's not just that dopamine is just hanging around because we had this big bolus of it released 20 minutes ago. Something else is going on that is actively maintaining dopamine levels high. So then we started looking at, what's going on? Why should there be an activation of ongoing release process when we're no longer stimulating and the animals are resting peacefully in their home cage now?
So what did you do next?
With that in mind, we started collaborating with Susan Amaro's lab, and I had heard that they had this, at the time, this mechanism where if you introduce a big bolus of dopamine in the area of the brain striatum that we were measuring, or slices from that area, what they would see is that dopamine transporters, which are molecules that take dopamine inside, they internalize. They go inside the cell, so they're no longer active. First, we found that in an in vitro preparation, we could see an activation and we could block the dopamine transporter with a compound that was shown in vitro to block it. So then we went to in vivo and we showed that, in fact, that happens in our in vivo findings, that if we give the drug that stops dopamine transporter internalization, we also stop that lingering amount of dopamine.
What does this mean? What's going on?
Normally, when dopamine cells are firing, they're releasing a certain amount of dopamine, and some of it is taken up by the dopamine transporter that to kind of keep a steady level of dopamine release. When you have a situation where there's burst activation of dopamine, such as when you are trying to learn something, when you are working to get a reward, all those contacts make dopamine cells burst. Then you have a big bolus of dopamine that's released. What that giant release of dopamine does is it causes the dopamine transporter to internalize, therefore deactivating it. So there are a lot fewer dopamine transporters now to take up dopamine. So when you go back to a rest situation, which is post-learning, going back to your home cage, when dopamine cells go back to firing the way they were before, a lot more becomes available because dopamine transporters aren't there to take it up. So the same amount of dopamine cells firing is now having a bigger impact at the terminals, is causing a bigger availability of dopamine.
Why is this important? What does dopamine do as it stays around?
Well, it's really important because dopamine is critical for a number of functions. It's important for setting up your background state of motivation. or anxiety, depending on where the release is happening. So dopamine lingering can be a big deal. I mean, one of the reasons people are prescribed Ritalin is potentially to keep more dopamine lingering around because it's preventing the uptake of dopamine. And we also know that dopamine is important for learning. And there were these studies that were done, they started in the 60s, but 70s, 80s, they were completed, that if you trained an animal on behavior tasks, so they had to learn something new. And during the training, if you gave them a dopamine receptor blocker up to 15-20 minutes after training, the animals couldn't learn. The next day when you put them back on the Skinner box or the maze, they hadn't learned. So somehow you had this window of time post-training that dopamine must be lingering around and be critical for learning and memory consolidation.
Dr. Moghadam's new study might explain how the brain keeps dopamine so important to all these processes around.
So even if you stop studying and you're pausing afterwards, dopamine is out there working for you to make sure the memory consolidation happens. It could also be a way that after a context like stress or other things that elevate dopamine firing rate, dopamine levels could stay up to increase your motivational level higher in order to do whatever you need to do to enhance your chance of survival. So we think it's a mechanism to actually keep dopamine levels elevated for 20, 40 minutes after a context that forces dopamine cells to burst.
In the paper, you write that there are implications for understanding dysfunctions of dopamine, conditions such as ADHD, addiction, schizophrenia. What are some of the implications there?
So dopamine transporter molecules, the genes, there's several allelic variations of dopamine transporters that are implicated in ADHD. Hypothetically speaking, if let's say you have one of those alleles or a form of dopamine transporter that doesn't internalize as readily, that means that you don't have this nice post-stimulation dopamine activation that could allow you to focus, pay attention, or remain motivated. So, you essentially have this reduced activation of dopamine that's very stimulation dependent. I think it has tremendous relevance to ADHD because the dopamine transporter molecule has been implicated in the genetics of ADHD. So if there is any change in dopamine transporter internalization, if the dynamics of that internalization is different, then you essentially have less dopamine around after burst activity. And that less dopamine could mean impaired ability to pay attention or reduced motivation. With other illnesses that are dopamine dependent, again, if this mechanism is regulating dopamine homeostasis, too much of it could cause hyperactivity, psychosis, and too little of it can cause cognitive deficits and, again, reduce motivation, reduce attentional tuning.
What were some of the weaknesses with your study, and what research do you think needs to be done next?
We were limited by the methods we could use to show faster activation of dopamine. We were limited by how we could actually test the fact that if we block active release, a dopamine release goes down. We have very few tools that we use here with TTX. And ideally, you want to show this in a behavioral context. For example, show that if you block this mechanism, then learning is inhibited in correlation with activation of dopamine. That last one is not a weakness, but that's something that could really help with the mechanism and the hypothesis.
Dr. Moghadam says that's the next step to understand the behavioral function in the brain.
The next is to see how relevant this is in behavioral context. It would be very cool also to look at some of the mouse mutants that have some of the dopamine transporter deficiencies that has been found in schizophrenia or ADHD.
She also says computational models used today assume a linear relationship between dopamine production and the dopamine transporters, and the models should be studied to incorporate this nonlinear relationship. This is the podcast for the journal Neuropsychopharmacology. To read the research paper discussed in this podcast, go to www.nature.com/NPP. I'm Cynthia Graber.